In this video we're going to look at our second extension to the simple functional. So the simple functional, as a reminder, is going to be the integral of our function f with our independent variable x, with our y and our y derivative, all by dx. Now we're going to extend this here, but instead of having just one derivative of the value of y, we're going to have a second derivative of y and a third and a fourth. And in general, we could say we're going to derive it up to the nth derivative of y. So we're interested in looking at this functional form here. Now what we'll do is we'll talk through this video in a bit more detail than maybe you've seen in some other videos. So some of this will actually be a reminder of what we've done in the previous course, but it's well worthwhile just talking through it just as an aid to learning. So for our simple functional here, we said that we're going to start off with the value of our extremum, which is our y of x, and we're going to add on a variation. Now we added on the variation by taking a family of curves, and the curve we've got here is the eta x. So that's our family, that's our curve here, which is in the solid pink, and we're going to multiply that curve there by a factor epsilon, so that's just a constant. So by multiplying it by that epsilon, we're going to generate this family of curves epsilon eta of x, and what we do is we add the epsilon eta of x, so this is our variation, and we add that onto our original extremum. So we get this new curve up here, which is the blue curve. And this blue curve here is large y of x, which is equal to the original extremum small y of x plus the variation epsilon eta of x. So that should be stuff that you've done before, so that should be revision from the previous course. Now our function eta of x is just an arbitrary function that we choose. The value of eta of x at this point here is 0, and at this point here is 0. So we could call that point A, and this is point B. So we can say eta of x when x is equal to A is just equal to 0. So we can say eta of A is equal to 0, and also eta of B is equal to 0. And we can also say the rate of change of eta with respect to x at A is equal to the rate of change of eta with respect to x at b, and that's also equal to 0. So the rate of change of eta is also equal to 0 at that point. So we've got this set up here. Now the only thing that causes a variation in this function is the choice of epsilon. So as we change epsilon, it changes this last function y of x. So if we're looking to differentiate this function here, we have to differentiate it with respect to epsilon, because that's the only thing that we're allowed to vary. So if we were to differentiate this function here with respect to epsilon, we're going to have d by d epsilon of the function large y of x, which is equal to small y of x plus epsilon eta of x. So we've got our small y of x plus that should be epsilon eta of x, so I'll put the epsilon in here, so there should be an epsilon here. Okay, so we're going to have an epsilon eta of x. So whenever we go to differentiate that, we're going to have, first of all, we're going to have our d by d epsilon of our y of x, and this thing here is a product of two functions. So we've got a function of epsilon, because we're going to have epsilon, and we're going to have a function also eta of x. So what we can do is we use the product rule for differentiation. So we differentiate the first one, multiply it by the second, then differentiate the second and multiply it by the first. So we could have d epsilon by d epsilon. So that's our first differentiation, and then we multiply it by the eta of x. And then we're going to have to differentiate the eta of x with respect to epsilon, and then we multiply it by the epsilon. So we're going to have these three terms here. So we can call this here term 1, and this term here would be term 2, and this term here would be term 3. Now the thing about these terms here is we can note down below that the value y here, well, y is not a function of epsilon, y is a function of x. So whenever we differentiate y with respect to epsilon, we're going to get a value of 0 because it just isn't a function of epsilon. Now this term here, d epsilon by d epsilon, well, that's a simple of 1, that's equal to the value of 1. So all we're going to be left in this term here is the eta of x. Now the third term here as well, we're going to have d eta of x by d epsilon. Now we can see here again that our eta is not a function of epsilon, it's a function of x. Now the way you can think about this is that we choose this value of eta of x, so we choose this function. Okay, so this choice of function has happened before we even introduce any variation, and we could choose a different one or a third one or a fourth one, so we choose this. So the choice of this here is not affected by the value of epsilon. So eta of x is not a function of epsilon, so this term here can disappear. Okay, so we're just going to have this term here will go to 0. So all we're going to be left with is the eta of x. So therefore we can say that our dy by d epsilon is equal to the value of eta of x. So we've seen that whenever we differentiate our y with respect to epsilon, we get our eta of x. Now we can do the same thing for our y derivative. So if we differentiate our y derivative with respect to epsilon, we get the eta derivative of x. Now this is revision. You'll have seen it in the very first video on the video series here, and also if you've done the first course you'll see it whenever we derived the Euler-Lagrange equation. So what we want to do here is in effect derive another Euler-Lagrange equation, but instead of being the Euler-Lagrange for this simple functional here, it's going to be an equivalent Euler-Lagrange for this functional form here. So a functional that's got higher derivatives. So let's go ahead and we'll do that in the next page. Now if you get stuck as we work through this video, you can also go back to the derivation of the Euler-Lagrange equation, which is in one of the very first videos of this video series. So we're going to simplify our nomenclature here. We have the extremum plus the variation, which is the large y of x. Now we know that the y is a function of x, so we don't need to keep putting down the x term here, so we'll just write that as y. And we'll find the first derivative and we'll write it down as y dash. The second derivative will be y double dash. The eta of x, again, we'll just write that as eta. The first derivative we'll write it as eta dash, and the second derivative we'll write it as eta double dash. So we're going to work through the example first of all with just the second derivative, and then we'll generalise it up to the nth derivative. So if we write down our variation, so our variation is going to be our delta I, it's going to be the original functional here, and it's going to be the functional plus the extremum. So if we take the original away from the new one, then we're going to get the variation. So we can rewrite this out here as the first term in a Taylor expansion. So don't get lost here. If we had a simple function here, there's a simple function of y, there's x and there's y, then again we can find the rate of change of the function at this point, and we can multiply that by the distance along here, and it's going to give us the first approximation here, which would be this height here. So this would be the first Taylor approximation. A second Taylor approximation would be epsilon squared upon 2 factorial. So in this simple example here, we would have the gradient of this function. Let's say we call it df by dx. So that's the gradient at that point. If we multiply it by this little distance here, now this little distance here is, call it epsilon. So we'll get df by dx times epsilon will give us this height here. Okay, so this is going to be our first Taylor approximation. But of course, we're not doing it with a simple function. We're doing the whole thing with a functional, and this is the functional form above. So we know that whenever we do the differentiation here, it's not just simply a case of our df by dx. We're going to have the differentiation of our functional form, which is given above. So we know that we're going to have to differentiate this here, and we know that we're differentiating the function here with respect to the only thing that causes the variation, which is the value of epsilon. So we're differentiating this thing here with respect to our value of epsilon. Now, in order to do that, we can say that the function f here is going to be a function of y, but then the y is also going to be a function of epsilon. So we've got to use the chain rule for differentiation. So we're going to have our partial f by partial y times partial y by partial epsilon. And then we're going to have our partial f by partial y derivative times partial y derivative by partial epsilon. Now, we've seen this before whenever we derived the original Euler-Lagrange equation. But now we're going to add the extra term in. So the extra term in here is going to be partial f by partial y double derivative, and I'll just call it double dash, times partial y double dash by partial epsilon, and that's all by dx. And of course we're going to have the higher order terms here as well. And of course in this here we don't differentiate x with respect to epsilon because x is not a function of epsilon. X is just our independent variable. So we've got these three terms here, and again we've seen this before when we derived the Euler-Lagrange equation, but we've already seen that our partial y by partial epsilon is going to equal a value of our eta, and our partial y derivative by partial epsilon is going to be eta derivative. Now, by extension to that, if we were to look at partial y double derivative by partial epsilon, we're going to get the value of eta double dash. So we're left with this equation here. Again, if you look at the derivation of the Euler-Lagrange and compare it to that, with the Euler-Lagrange we would only have had these two terms here. Now when this extremum delta I is equal to 0, we know we're in an equilibrium position, so we set this here equal to 0. And again, from the original derivation of the Euler-Lagrange, we want to take these values of eta x out of this equation here, and we want to be left with something within this bracket here. Now whenever we take the eta of x out, we know that eta of x doesn't equal 0 because that's the function that we use in order to generate our variation. So the thing that will be left inside the brackets will be the thing that is equal to 0, and that will be our Euler-Lagrange equation, but our Euler-Lagrange equivalent for this type of functional. Now we've seen whenever we derive the Euler-Lagrange, we have to separate these eta and eta derivative and eta double. Now that we've got the eta double derivative, we'll have to take out of this bracket. Now we can take the eta out, but we can't take the eta derivative, so we need to change this. So we've only got an eta here and we've only got an eta here. So we do that by using integration by parts. So we'll have to do integration by parts on this one here, so we can call this 1. And we're going to have to do integration by parts on this. But this here has got eta double dash, so we're going to have to do integration by parts on this twice. But we'll do this one first, or below, and then on the next page we'll do this one here. So as a reminder for our integration by parts is like the product rule for differentiation, but it's like a product rule for integration. So if we had two functions here, the integral of u times dv, we could write that as equal to u times v minus the integral of v du. So that's our integration by parts, and that should be some revision for you. So if we say in this case here we let our value of u equal this term here, which is partial f by partial y derivative, and we say that the value of our dv is equal to our eta derivative, then if we were to integrate this dv, then we would have the value of v, and it means on the right hand side instead of eta dash we'll just have eta, so we can say that our v is equal to our eta. So substituting the values in for our integration by parts, we're going to have u, which is partial f by partial y derivative, that's this term here, times the value of v, which is our value of eta, and we're integrating that from b to a, and it's going to be minus the integral from our a to b over v du. So our v here is going to be our eta, and our du here is going to be, well, the u here is partial f by partial y derivative, and we're differentiating it here, in this case here with respect to x, so it's d by dx, and that's all by dx. So this is our integration by parts, but we know that the value of eta at a equals the value of eta at b is equal to 0. So this first part here is going to cancel out, so we're only going to be left with the part at the bottom, this part here, which is minus the integral from a to b of eta d by dx partial f by partial y derivative. Now I've gone through that in a lot of detail here, and as we've seen in the previous course and through snippets in this course, we could actually do this just simply by looking at it once you get used to doing integration by parts. So I could quickly look at this part here, and I could say I don't want the eta derivative, I only want an eta term, so I use integration by parts. First of all, I make the plus sign a minus, so that becomes a minus, and we've got an integral from a to b, and the thing that is outside of this differential here, we now want to put it inside the differential, so it means that our partial f by partial y derivative goes inside the differentiation, so that's inside the differentiation here, and the thing that is inside the differentiation in fact is our eta dash, then goes outside the differentiation, so the eta dash then becomes just the value of eta. So once you get used to using integration by parts, you can quickly look at these and instantly in your head just do the three things that you need to do in order to get this answer here, and it becomes quite simple. So let's go ahead and we'll look at the next value here. We need to get rid of the eta double dash, and it has to be again that come out with only the eta value. So now we're wanting to change this term here, so we want to get rid of the eta double derivative. So just as a reminder, we'll head to the previous page. We want to get rid of this eta double derivative, so we're taking this term here and we're going to change it, okay? So our eta double derivative partial f by partial y double derivative by dx, we have to perform integration by parts on this twice. So whenever we perform the integration by parts on this twice, we're going to be left with our eta dash partial f by partial y double derivative from a to b minus eta d by dx partial f by partial y double derivative from a to b plus the integral from a to b to eta d squared by dx squared partial f by partial y double derivative all by dx. Now that's an exercise for you to go through the integration by parts twice and see that you get these three terms. So again, the first term here is going to disappear because our eta of x at our eta derivative of x at a and b is equal to 0. And also this term here is going to disappear because our eta of x, a and b is also equal to 0. So we're going to be left with this final term here. So we're going to have this term here, which we're going to have to put into the original equation. So it means whenever we put the two terms back into the original equation, we're going to be left with these three here. So this one here is the remains the same. So I'll just go back into the previous page so you can see. So this term here remains the same. This term here gets replaced with this term here. And this term here is going to get replaced with the term which we've just derived above, which is this one here. So we're going to be left with this here. Now you can see here now that we've got only the terms in eta, eta and eta. So that's the reason for doing this differentiation by parts. It allows us to take the eta out of this bracket. So we're going to be left with the eta of x. Eta of x is the curve that we've chosen in order to generate a family of curves which we can use to create the variation. So this thing here is not equal to 0. If it was equal to 0, we wouldn't have any variation, and the last half an hour of mathematics just wouldn't have happened. So we take this out, and what's left inside the bracket in effect becomes our Euler-Lagrange equation. And I use that advisedly because it's not the Euler-Lagrange equation, but it's an equivalent of that for this different type of functional, a functional with higher derivatives. So it means that the thing inside this bracket here must be equal to 0 by the fundamental lemma of the calculus of variations. And again, if you want to check the fundamental lemma, you can go to the first course where we've got that derived, and we'll also go through and I'll show you the fundamental lemma graphically in the graphical calculator. So this here is our differential equation that will have to be satisfied in order to ensure that we actually have an extremum. Now this is for our value for our derivatives going up to the second order. So if you like, you can say the order of our derivatives is an order of 2. So we're going to have a y derivative and a y double derivative. But what's going to happen whenever we extend this and generalize it up to an nth order derivative? Another thing finally to note here, that I've written this in terms of small y as opposed to large y, because as the value of epsilon tends towards 0, the large y of x tends towards small y of x. So let's go ahead over in the next page and we'll see what happens when we extend this to n derivatives. So if we take the equation in the previous page and we extend it up to the nth derivative, then we're going to have this equation here. So this is their first term, second term, third term, and then if we work through all along the nth terms, we're going to be given by this final term here. And of course that is all equal to 0. Now we're not going to work with this general nth derivative because it's going to be too complicated. So we're going to stick with just the n is equal to 2. So we're going to look at the y derivative and y double derivative. So we're interested in the necessary and the sufficient conditions for our extremum. So the conditions for a minimum and maximum, and this is just stated below. So I've not gone and proven this. So again, this is just a statement. So if the equation above is satisfied, so we're actually satisfying this for only n is equal to 2. So we're only doing this term, and this term here. So we're using a functional of the form y derivative and y double derivative. Then we can say then that if this is satisfied, then we will have an extremum. So remember, this would be equivalent to our Euler-Lagrange, but for this new functional type. So if it's equal to 0, an extremum does exist. So we need to find out what that extremum is. Is it a maximum or a minimum? And we know that from our theory and conjugate points, we want the conjugate point to be out with the interval AB. Then if the value of our partial squared f by partial y squared, which in effect is this second term here, doesn't change sign on AB, then we can say that if this term here is less than 0, then our extremum will be a maximum. If this term here is greater than 0, our extremum will be a minimum. So a lot involved in that video, but I went through it in an awful lot more detail than I would normally. I think sometimes it's good just to go through in detail as a recap for your learning. So that's all for this video. I'll get you on the next video. Goodbye.